Hey everybody, thanks for joining me today. I'm going to be talking about weather. I got a request to do this a while ago and I'm just now getting to it, so my apologies. It's the time of year where I live for a transition into more tumultuous weather in the form of thunderstorms, tornadoes, and eventually hurricanes in the northern hemisphere. And I have this book, very old, very loved, Weather and Climate. So climate is different than weather. Climate is actually the weather patterns in a particular area over a duration of time, and they're pretty stable. The Earth does have heating and cooling phases, but since you've been born, the climate has been pretty stable wherever you live. For instance, in the Arctic, it is a polar climate, and near the equator, it is a tropical climate. There is a gradual warming of the Earth right now, but it's very gradual. And the climate, since you've been born, has relatively stayed the same. Now, weather is the atmospheric conditions in a particular place at a given instance. So we have weather at this moment, weather for today, that kind of thing. So I'm gonna focus on thunderstorms and tornadoes, but I kind of need to give a little basic introduction into the cycling of air masses and things like that on Earth that give us our weather patterns. If the Earth was not moving or rotating, or if it wasn't tilted on its axis, we would have stagnant weather. But we know this is not true. The Earth is tilted on its axis. So as it goes around the sun in a year, in the summertime, for the northern hemisphere, the northern hemisphere is tilted towards the sun, receiving more direct sunlight. And the southern hemisphere is tilted away from the sun, receiving less direct sunlight, and they're having their winter. In the winter solstice, at the winter solstice, the northern hemisphere is tilted away from the sun, and the southern hemisphere is having its summer. It's tilted towards the sun. So, because of the tilt, there's uneven heating in the northern and southern hemisphere, and because of the shape of the Earth, it's round, as we know. More direct rays hit the middle of the Earth because it's bigger, so it reaches them faster. The poles are harder for the sun's rays to get to, so they're weaker at the poles. And makes sense. Near the equator is getting a lot more direct sunlight and it's warmer. The warm air at the equator moves around the Earth though and helps to warm places that would otherwise not be warm. And it does this through water streams like the Gulf Stream and through wind patterns. So I'll explain that in a moment. As you know, you probably know, the Earth has an ozone. This is a layer that around the Earth that basically prevents all the sun's rays from hitting the earth, because otherwise we would be cooked. It absorbs some of those rays for us. And it lets out some of our gases. Now, if the ozone was too thick, like Venus, and our gases could not escape, we would not sustain life here on Earth. And if we didn't have an ozone, like I said, we would be toasted. So it's a very delicate balance that we have achieved here on Earth, and I think that's pretty cool. So under the ozone is the atmosphere, the gases around the Earth, held close to the Earth by gravity. Our atmosphere has a lot of nitrogen in it, some oxygen, carbon dioxide, and a lot of water, a lot of moisture from evaporation. As you guys know, oh, that's the wrong page, my apologies. We have the water cycle. Water vapor is evaporation of surface water. The earth is mostly water, so there's a lot of evaporation going on. This moist, warmed air rises to the top because it's very low density, and then it cools. The winds blow it to other areas where it cools and condenses, becomes heavier, becomes too heavy, it falls back to the water in the form of precipitation, snow, hail, rain, sleet. Right. And water is essential to the weather machine. Like I said, air is in constant motion. It's warmed by the sun, and water is warmed by the sun. Ocean and large bodies of water hold on to heat better than land, so it's usually cooler over the ocean. But basically, the reason warm air rises, or warm vapor from the ocean rises, is because of kinetic energy. As the sun heats the air, the ocean, the water vapor or water molecules or the air molecules become hot, and this gives them a lot of kinetic energy and they start moving around. They need more space, so they get more space, which makes them less dense. Cold air, the molecules are closer together. They don't need as much space, so they're more dense. They sink. So if you have air rising, air sinking, being blown by wind, you have warm air from the oceans that's wet, rising and being blown to different areas. You have the earth spinning, Coriolis effect. This basically means that air cannot directly move north to south. Winds blowing from the poles to the equator are shifted westward, because that's the way the earth is spinning and it's pulling some of that air. This gives us our weather, more or less, right? And the swirling around of the cold and warm air masses is known as convection. And when warm air rises, something needs to take its place. So you either have more warm air come in, where you have cold air come in, depending on what's nearby, what time of year it is, etc. So I have a picture of that in this other book that I have. A lot of cold air from the poles move in the northern hemisphere south. So the blue in this picture are cold fronts coming from the poles, and the red are warm fronts coming from this equator. Okay. Now, because cold fronts are denser, they're also considered high pressure and pretty stable and dry. The warm fronts usually carry more moisture, and they're very unstable, and they're low pressure. So you hear low pressure system, high pressure system. When these two collide on a front, it can cause thunderstorms and tumultuous weather. Right? The earth, the water, they're not heated uniformly. So, one cool thing to note is that the water above the Gulf Stream, which comes down, as you can see, the warm weather around Florida here, the warm water, the Gulf Stream carries warm water all the way up through like North Carolina, and because this warm water is causing evaporation, warm air, it brings warm rains, it brings warm air to places. So that's pretty cool. The water can affect the weather very much so. And it has the same properties as air, in that when warm water is blown to another area of the ocean, something needs to take its place. So the cold, dense water underneath it will rise up. That's called upwelling, and it's very common on the west coast. And it makes the waters on like the west coast of the United States, the water is actually colder, more nutrient, it holds more oxygen, but it's colder. Now, when the winds stop blowing the warm water away and the cold water rising ceases, it wreaks havoc. And the warm, moist water that's being blown away is being blown straight into Australia and other areas where they receive lots of rainfall. So during years when the upwelling ceases, those areas experience droughts. The earth is always trying to achieve balance. Where there's a drought one year, there will be lots of rain the next. Where there's lots of hurricanes one year, there will be less hurricanes the next. Always achieving balance. Now we're going to talk about thunderstorms. Let's start with hurricanes. A hurricane is basically a thunderstorm above the water. It's called a typhoon in the Pacific. I'll show you a picture. So, during summer and fall in the northern hemisphere, the water's warm. And it takes longer for them to warm. And it takes longer for them to cool. So they get hot by like the middle of summer, and they stay hot through fall. So you have a lot of moisture being pulled up into the atmosphere, right? And so hurricanes basically start as small thunderstorms, but as warm, moist air is rising up into the atmosphere, instead of cold air coming in and taking its place, more warm, moist air just keeps feeding into it and rising and feeding into it. And it's sucked in and it causes a whirlpool, like the picture that I showed you. I'm gonna find another picture. And you know, it's considered a low pressure system because warm, moist air is considered low pressure system. Here we go, hurricanes. It draws energy from the warm water. It can actually release as much energy in a day as 500,000 atomic bombs. So hurricanes are intense. They kill more people every year than all other storms combined. Oh, where'd it go? I'm trying to find this picture again. Here we go. So it shows the middle of the hurricane pulling up hot, moist air, right, into it and swirling around. It can blow between 74 to 240 miles per hour. When it hits land, the initial part of it that hits land first is known as the storm surge, and this can cause extensive flooding. And it does weaken as it hits the earth, as it hits land, because it doesn't have, it relies on the warm, hot water, the warm, moist water for its energy. So once it hits land, it loses its energy. But it brings all of that hot water that rose into the hurricane is going to be released onto the land, and it can cause massive flooding, and the winds can be very tumultuous. Hurricane Andrew in the United States in 1992, $1 billion worth of damage. So they're something to be taken very seriously. I used to live on the coast, and I was in a few hurricanes myself, and they were level 1 or 2. I think Andrew was a 5. They have to exceed winds of 39 miles per hour to be considered a hurricane. 39 miles per hour and below is just a tropical storm. They have as you saw in the diagram, a calm center known as the eye, where it's dry. That's the suction cup that's pulling up the stuff in the water. And so when it hits land, it's very like an eerily calm part of the hurricane. And it's very eerie. If any of you have been in a hurricane, feel free to comment. So let's turn our attention to thunderstorms. I'm going to show you some clouds. Okay, so we have the ones that are most common, I think, are the cumulus. They're the big fluffy clouds. I call these stratus, but they're stratocumulus. And the stratus are just like wispy, and stratocumulus are between stratus and cumulus. These ones kind of look like plain trails, cirrocumulus. And these, cumulonimbus, are the storm clouds. They're basically hot, moist air that rise fast enough to form thunderheads. It has to be a fast process, meaning that if it gets really hot during the day somewhere and there's a lot of humidity, it can rise really fast and you'll feel the pressure drop as this low pressure system is moving upward. Barometric pressure drops. It can rise so far up into the atmosphere that it condenses very quickly, and it cannot hold all that water all that moisture once it condenses, so you get a large amount of rainfall. Now if conditions are right and there's a cold front nearby, it will collide with the updraft of the warm air and create a downdraft. And I'll show you a picture of this. And this is going to make the swirling up and down inside of the water vapors and air inside of those thunder clouds, and it's going to cause protons and electrons to build up in different areas. There are electrical charges on a lot of things, tall buildings for instance, but the air is pretty insulated. However, there's so much friction in the thunder clouds that the electric difference causes an electric burst, lightning, to move from an electron to a proton. Now this can move in between the clouds, or it can move from the cloud to a tall structure on the ground that has built up protons on it. So the thunder is actually when there's an electric surge from electron to proton. It's so hot and fast that the air around it becomes so hot and it moves very quickly in each direction, and it creates the sound of thunder. That boom is the movement of the air around the lightning bolt. So you see the lightning before you hear the thunder because you see things before you can hear them. Light travels faster than sound. So for hail to be produced, those water droplets that are, like I said, those clouds are built very quickly and they go very high up. Let's see if I have a figure here for you. I thought that I did. I don't see them. Hundreds of millions of volts is the electricity of light. 50,000 degrees. Extreme heat causes boom, expansion at supersonic rate. Yeah. Okay. So, it does not say how far up the, doesn't say how far up the clouds go. but it goes up high enough for ice crystals to form. And they fall because they're heavy. But remember I said as things are moving up in the cloud and condensing, things are also falling, and it creates that spiral, so the ice can get sucked back up and another layer of ice added to it, and it starts to fall, and then it gets sucked back up, another layer of ice added to it. So the more tumultuous the air inside of the storm is, the larger the hail. That's why it's sometimes associated with tornadoes, which I'll touch on in just a moment. So, thunderstorms can bring flooding, winds up to 60 miles per hour, I believe, and damaging hail. Yeah, so lightning can be very dangerous, and they're up to 16 million thunderstorms each year. And there's lightning going on somewhere in the world right now. My book on tornadoes, and then I will have a follow-up video where I make a tornado as requested. Okay. Tornadoes. Tornadoes can top 300 miles per hour. There are 800 through the US every year. Why is the US such a good place for tornadoes? Because, like I said, air patterns. There's warm air. This shows tornadoes around the world where they're common. In the United States, warm Gulf air moves up and collides with cold polar air. The land is flat. There's no mountains in the way. In the Midwest, the Tornado Valley. And so as warm air flows one way and cold air flows the other, and they hit each other, it starts to spiral in between them. They collide. The warm air moves up. It pulls the cyclone with it into the air. So that's what happens when there's a front where the cold air and hot air hit each other very rapidly. The air starts swirling around, the hot air rises so fast it picks up the gets pushed up and twisted as a rotating column of air gathers force. When rain cooled downdrafts hit warm air near the ground. Okay, so this shows it starts to rain and cool things off, and as the hot air rises and it pulls up this supercell, the cold air is coming back down. Remember, there's hot air going one way and cold air going the other. And if it pulls down right at the back of that cyclone, it's known as the rear flank downdraft. It will pull the cyclone back down and touch the ground, and you have a tornado. The suction inside of it can be so strong it can lift trees, cars, houses, and redeposit them. And so it's pretty dangerous. Okay, so here's the hot air being sucked up, the cold air coming down, downdrafting. Now, because the hot air is pulled up so fast, it cools, and like I said, the rain is always pretty heavy. Ice crystals form. It can go down and get sucked back up and go down and get sucked back up because the vacuum inside of it is so quick. So I'm gonna show you my own twister. They can last 20 seconds to an hour and they kill about 90 people each year in the United States. They're measured by a, I don't know how to pronounce this, Fujita scale? Excuse me. And this shows some record killing tornadoes. Actually, pretty recently in the US, we had a strand go through Georgia. We had one in Kansas, I remember, that killed many people. So, and I actually have been in a tornado before. If you're ever in a tornado, if there's a tornado watch, remain alert. Tornado warning, seek shelter. Go into an underground protection if you have it where you live, or go to the first floor, bathtub, seek shelter, line a ditch if you have to, if you're in your car. And that, my friend, is tornado safety. That is all I have for you. Weather is not my forte, so I did struggle a little bit in trying to explain weather patterns to you, and if it totally bored you, I apologize. The next video will be way more fun, I hope, but thanks for watching, guys.